All right, so now we're going to talk about computing. Well, I'm just going to do the sine of theta now, but you should be able to play this same game for any trig function. We're going to compute the angle of sine of theta when theta is not given to you directly as a number, but indirectly in the middle of a diagram in which the various sides are given to you. Okay? So here's the first example. Let's compute the sine of theta when theta is this angle right here in this triangle right there. Okay, so this is a triangle which has a near side of 2 and a long side of 4. Theta is this interior angle. And so, of course, using the definition of the trig functions, we know that the sine of theta, just working from nothing in this case, is by definition the opposite over the hypotenuse, which in this case is equal to 4. Our problem is we need to know what the opposite side is. Our solution to find the opposite side is the Pythagorean theorem. The Pythagorean theorem tells me that 2 squared plus the length of the opposite side squared is equal to 4 squared. From this I deduce that the opposite side squared is equal to 12 after all the dust settles, and so the opposite side is equal to 2 times the square root of 3. Therefore, I deduce up here that this is equal to 2 times the square root of 3 over 4, or just to be nice and simple, wait a minute, this is the square root of 3 over 2. And even though this is a highly planned out video, I accidentally just drew a 30, 60, 90 triangle up there for you. At least the side dimensions where I know what I was doing. In any event, there you go. See, the 30, 60, 90 stuff works. Okay. Let's move this up a little bit though. Now I want you to compute the sine of theta when theta is given to you as the angle whose secant is equal to 7/3. And now this is a little weird because there's a whole bunch of thetas, right? So let's look at this, right? What does it mean for the secant of theta to be equal to 7/3? Well, this means one triangle which does it. Since secant of theta is equal to the ratio of hypotenuse over the adjacent side by definition, right? I could draw a triangle whose hypotenuse is equal to 3, whose hypotenuse is equal to 7 and whose adjacent side is equal to 3, leaving again me to wonder about what the length of this opposite side is. As in the previous case, to find the sine of this angle theta, I need to figure out the ratio of opposite over hypotenuse, and for that, I use the quadratic formula. The quadratic formula in this case tells me that 3 squared plus the opposite side squared is equal to 7 squared, and so I deduce that the opposite side's length is just the square root of 40, also known as 2 times the square root of 10. Now, from this, I can see that the sine of this very same angle is equal to, and it's 2 times the square root, of 10, is equal to the hypotenuse, which is 7, divided by 2 times the square root of 10. This is one answer, but interestingly enough, this is not the only possible answer. Theta was just given to me as a theta which solves this equation, but of course, the theta which solves this equation doesn't just have to form a triangle of this form, right? It can also sit on the unit circle on a different quadrant right here, right? Namely, it can live down here. You'll notice if I draw the same triangle up here, just shrunk down to be inside of the unit circle, okay, I get an angle that lives down here. So theta could have lived down here and still given me the same secant out, because secant only cares about, the ratio of adjacent over hypotenuse. This has a positive adjacent, as does this triangle. So both of these triangles both have positive secants, both have the same ratio, so either angle theta could work. However, what you'll notice is that the sine of this theta is different. It differs because the long sine here is negative. And so in fact, sine of theta can be equal to that, or it can be equal to negative 7 divided by 2 times the square root of 10. I'm going to give you more problems on this so you can contemplate that a little bit more. This is one of the harder ones to think about. But the point is just that there is not a unique theta which makes this true. There are lots of thetas which makes this true. And one of them gives you a positive sign, the other one gives you a negative value of sign, depending on which quadrant the theta lands you in. The final one is this weird one. So here we're given theta, okay, and this time it winds. It's not even inside of a triangle. It's winding around the unit circle, and it lands up here at a point. And what do we know? Well, this is not actually the unit circle in this case. I've actually screwed that up. This is actually the circle of radius 5, okay? And what do I know is that as this angle winds me through the circle of radius 5, it ends me on a point of the form -3y, where I haven't been given the y coordinate. However, the problem is nearly identical to what we saw before. What we do is we just extend this triangle down right here. And as before, the sign is going to be the ratio of opposite over hypotenuse. Luckily, if I pull this triangle out of here, what do I know? Well, unlike the unit circle, we're dealing with a circle of radius 5. We're dealing here with a hypotenuse that has length 5. The fact that the x value of this point is -3 tells me that the length of this side here is 3. And to compute the sine of this thing, I just need to figure out the opposite side length. And how do I do that? Again, Pythagorean. I know 3 squared plus opposite squared is equal to 5 squared, which chills me out to give me opposite length of 4. And I know that this is a positive coordinate here. So I know that y is 4, and therefore I know that my ratio of opposite over adjacent, sine of theta in this case, is 4 divided by the hypotenuse, which is 5. So this one gets a little bit tricky because it involves the wrinkle that we are not given points inside of the unit circle, but inside of the circle of radius 5. There are important lessons to contemplate in each of these examples. If you don't understand some of these steps, well, I'm going to give you a worksheet where you can think about it some more. But you want to figure this stuff out. Okay. All right. What I'm about to do is a little bit dirty. I'm going to prove the Pythagorean theorem right now. You can skip it if you want, but there might be a secret assignment in here. So let's look here. I'm going to prove the Pythagorean theorem. And the Pythagorean theorem, remember what it says. It says that a squared plus b squared equals c squared. When I'm given a triangle, a right triangle specifically, of side lengths A, B, and C as shown there. So you've seen this 1,000 times and maybe you don't know what this means. So to figure out how to prove a statement like this, we'll go back to the ancient Greeks. It's a very basic, well, it's not very basic, it's actually a nice cool theorem. It's the first theorem ever proved by a guy named Pythagoras, theoretically, supposedly. I don't know if it's actually true. But here's the point. The way they prove this things is visually. If you think about it, if this is my short side, what does a squared represent? It represents the area of this squared. What does b squared represent? It represents the area of the square down here on the bottom side. And what does c squared represent? It represents the area that you build with side length equal to the hypotenuse, right? So the Pythagorean theorem, what it's really saying is if you start with a triangle like this, and you build these squares off of its sides, then the area of this square plus the area of this square is equal to the area of this square. Now let's go about proving it. The proof of the idea is simple. The first thing that you're supposed to show, and keep in mind this is kind of a crappy picture. It probably ends like right around here, but in any event, whatever, I screwed it up. The point is just that I'm going to prove that this rectangle is equal to this rectangle, right? So if you draw this straight down this corner, I'm going to prove that this rectangle is equal to the area of this square. I'm going to prove that this rectangle right here on the other side of the big square is equal to the area of the big square right here. And once I prove those two facts here rigorously, I'll know the Pythagorean theorem is true. And here's the basic idea. What you got to do is you got to zoom in on these two triangles. Now here's what we observe. I claim that this triangle is equivalent to this triangle. In other words, I can just take this triangle and slide it over this triangle, and they will match up completely. In other words, those are congruent triangles. And of course, because my drawing is so terrible, I can't just rely on that. I can't rely on my eyeballs. And I gotta know this will work no matter what. So I gotta prove this using theorems. And so here's the basic idea, okay? I'm going to show that these two triangles are the same by showing that they satisfy the side angle side equality. And so what do I know? Well, because this is a square, I know that this side is the same length as this side. Likewise, I know that this side is the same length as this side. Right there, right? Finally, I know that this angle is the same as this angle. And why do I know that? Because both are made by taking a right angle and adding this smidgen. And this one, this is the right angle plus a smidgen, and this one, this angle is the right angle plus a smidgen. Therefore, no matter how I drew this, since these facts always have to be true, this triangle right here can always be twisted, and it will line up perfectly with this triangle right here. Therefore, this area right here is always equal to this area right here. And here's the tricky part. Remember that triangle formula, by the area of this triangle is exactly equal to half of the area of this square right here. Why? Because of the base times height. If we think of this direction as the height of this weird looking triangle, we know that base times height divided by 2 is the area of this. Therefore, 2 of these will give me the full area here. The same reasoning applies here. Okay? If I take this long side as my base and this side as my height, I see by base times height divided by 2 that this triangle has half the area of this rectangle up here, and therefore this entire rectangle is equal to this entire rectangle. So half of this square is equal to this part of the square is equal to this part. The bigger part, I use the exact same reasoning, just with different triangles. For this one, I draw this triangle right here. I use the same arguments to show that this is congruent to this outer triangle right here, that they can slide over. Even though this is a crappy picture, we know logically, had it been a good picture, we'd be able to know for sure that these have to coincide. And from that, we'd see that this area is equal to this area, and therefore, a squared plus b squared is equal to c squared.